participants to enter the lobby, and once he gives signal, then you can we can get started.
Okay, madam.
We can start, sir.
And we can start, sir.
Okay, thank you. Good afternoon to one and all. First of all, I like to thank Professor Dr. Nanowires for giving this opportunity to chair this session. I am very glad to welcome Dr. Hiroshi Watanabe, a professor from National Yang-Ming Chiao Tung University, Taiwan, for accepting to give the lecture, this session. I am very glad to share some information about his profile. Hiroshi Watanabe received his PhD degree from the University of Tsukuba, Japan, in theoretical physics in March 1994. He joined the corporate R&D center Toshiba Corporation from April 1994 to January 2010. His current position is a full professor, Department of Electrical and Computer Engineering in National Chiao Tung University, Taiwan. He has studied a wide range of science and technologies from quantum physics, semiconductor devices technologies, semiconductor memories, semiconductor nanostructures, electronic virus sensing, blockchain IoT, etc. He has around 155 granted patents all over the world. He has been a conference advisory board member of Flash Memory Summit and IEEE Technical Committee on Quantum Communications and Information Technologies. He has served as a fellow technical committee at Forme USA since 2019. He has been a senior member of IEEE since 2012. I hope his lecture will be very interesting and informative to all the audience. Okay, I welcome Dr. Hiroshi Watanabe to start his lecture.
Thank you very much for a very nice introduction for me. So now let me talk about the concept of electronic sensing of a virus. So my affiliation is the National Yang-Ming Chiao Tung University now. However, this university was the name changed from the National Chiao Tung University last month because the National Chiao Tung University and the National Yang-Ming University combined to be the National Yang-Ming Chiao Tung Universities. And there is a second author whose name is Si Nanowires. He was my PhD student. He is now working in Synopsys. And this work done by Loras and Corporation and National Chiao Tung University.
Sorry to interrupt you, Dr. Hiroshi. You haven't shared your screen.
Hello?
You haven't shared your screen.
Share?
So you should share your PPT screen.
Hiroshi, you have not shared your screen.
Okay. So, say, can you look at my PPT? No?
No, it is not visible.
Not it. How to do it? This one. Can you look at the PPT?
Now it is visible. Dr. Hiroshi, now it is visible. We can proceed.
Can you look at my PPT?
Yeah.
Yes,
now
yes.
it is visible.
Okay. Now
you can proceed.
Okay. So. Okay, now here is the scaling of the silicon nanowires. This is the top-notch technology of silicon technologies. So width of the thickness of the silicon nanowire is around less than 10 nanometer, typically 5 nanometers. Please remind that this thickness, the diameters. Okay, there is a typical size of bacteria, human cells, and hairs. And here is a virus. The diameter is less than around 100 nanometers. And silicon nanotechnologies are already arrived at less than 10 nanometer like this. Okay, so I think that we have the chance to combine biotechnology and silicon technologies for these aims. So here is a typical model of viruses. Size is less than 100 nanometers. And here is a human cell. The size is typically 10 micrometers. And this portion is receptors. And here is a spike on the envelope of the viruses. This spike and receptor can combine like this, can be combined like this. After that, they combine much more, and finally, so enter into the cells. This is the entry process. After that, viruses open the cells, and here is the nucleus inside the cells. Virus forwards his genome information to the nucleus, and the human body nucleus cells nucleus will replicate the genomes of the viruses. This is the replication processes. So you know these genomes come to the cell surface, and this is booting. And after that, he emitted the virus, new virus. Do it again, do it more. You know, this is the infections. So now here is the specimen with the viruses. Inside the human bodies, antibody will be generated to target the spikes like this. If the number of antibodies is good enough, we can cover all of the spikes like this. However, please remind that the number of spikes is 1,000 per 500 to the 1,000 per unit cells, unit viruses. In this event, no infection. This means that human body makes antibody much more the number of virus cells. Okay, in the specimens of viruses, not only the viruses, we have many non-specified proteins like this. So here is the genomes. Genome usually is RNA. RNA is made of AGCU. So using the detergent, we can break the viruses, and then there is many proteins inside the specimens. Among them, our target should be spikes, because this characterizes the virus. So the size of a spike is around same as the silicon nanowires. This is, in addition, the number of spikes is much more than the viruses. Therefore, we can detect the spikes, even though the number of viruses is not so much. We have a chance for that one, and we may use the silicon nanotechnology to detect the spikes itself. Okay. Now here is the spikes, non-specified proteins, and the membrane on which surface the antibodies or receptors are immobilized. Time has passed by the diffusion of the spikes. Some of the spikes arrived at the surface, and they are captured by antibodies, like this. After rinse it. In the ideal case, we can rinse most of non-specified proteins like that. And this is similar to this situation is similar to the biotransistors like that. So in the case of biotransistor, if we have the spikes, if the spike has electric charges, we can open the switch like this. If no spikes captured, in such a case, transistor is off. So this is on switch on state. This is switch off state. So characterization, this is a biotransistor. Now we have the two parameters to characterize the biotransistor's performance. One is the limit of detection, LOD, which is the lowest limit of detectable concentration of targeted spikes, target. If it is too high, the sensor cannot detect the targets, and even though they exist. If it is too low, non-specific noise is involved, not good in this case. And the second one is the detection time. If this is the time it is necessary to complete the diagnostic of the virus, whether or not the virus exists. If it is too long, the diagnostic is practically unable. Therefore, our aim is to lower LOD, shorten detection times by using the spike, because the number of spike is 1,000 times as the number of virus. And here is the definition of the LOD by Mark Reed. So here is dissociation equations. X is the concentration of the target spikes. Y is the concentration of receptors. Right-hand side of this, left-hand side of this equation, here is a delta VT. Delta VT is a transistor's characterization. So transistor's characterization. VT is called threshold voltages. Threshold voltage characterizes the transistors sensing performance. Left-hand side is electronics, and right-hand side biochemistry, because this is from the dissociation equations. Okay, so this work is potentially interdisciplinary. Okay, this is from the literature of FET-type biosensors. Now, this one is LOD, this is detection time. Our aim is lower LOD and shorter detection time. Therefore, our aim is here. However, from the literature, we haven't still arrived at this portion yet. Okay, now let's consider about the sensitivity of the bio-FET. So now let's take the top view. This portion is source, this portion is drain. This is the top view. This is the gate areas. Here is the gate insulator. On the surface of the gate insulator, we have a dotted. Dot I describe the dot is receptor capturing the spikes with charge. Okay. If the number of captured spike is good enough, in such a case, this transistor senses the spikes existence of virus. However, if the concentration is not enough, in such a case, insensitive. So next, let's consider only one charge exists here. As a property of the transistors, current transport get around the ion charges. In this case, insensitive. Okay, in order to overcome, in order to remove the chance of get around, we may shrink the width of the gate areas. For example, in this case, current cannot get around and the current speed is down. We can sense it in this case. Okay, so now here is one of the experimental examples. Now here is silicon nanowire, length is 1 micrometer. And this data is conductance of silicon nanowire FETs. Conductance is raised up by increasing the pH like this. If the pH is changing, the spike has the charges out of the isotropic point. Okay, now here is a one silicon nanowire and several spikes with charges. In this case, here is one spike captured by nanowire, may be sensitive. In this case, less concentration of spikes. In such a case, this is not sensitive. However, spikes floating inside the specimen, he may wait sometimes, and he diffuses and sometimes arrive at the nanowire surface, and he can be sensed like this. However, in this case, we have to wait until it is to be sensitive. Such kind of latency must be in proportion to the average distance between spike and the nanowires. In order to reduce the latencies, we may reduce the average distance between nanowire and the spikes. How to do it? This is the next idea. If you use a multiple nanowires, in such a case, we can reduce the average distance. However, we still have another problem. Okay, please remind that capital N is nanowire numbers. M equals to, in this case, this is a nanowire detecting the charge by target spikes. Okay, in this case, signal from this nanowire is I. Signal from this nanowire, I minus delta I minus delta I, and I, like this, in this case. Now let's calculate the ratio of the signal with or without nanowire, with or without spikes. This is difference. Difference is in proportion to 1 over capital N. Capital N is a nanowire number. In order to reduce the average distance, N must be increased. However, if N is increased, ratio of distance change is reduced. This is unsensitive. This makes it unsensitive. Well, I mean, we have a trade-off here. Okay. Now let's return back to the definition of the LODs. By using factor N over M, well, I mean, LOD must be increased for multiple nanowires. If nanowires number is increased, LOD must be increased. Our aim, please remind that our aim was to reduce LOD. Okay, this is a problem. Okay, now here is a trend like this. If the nanowire number is increased, LOD is increased. However, in this case, we can reduce the detection time. If nanowire number is decreased, LOD is decreased. However, detection time is increased. This is a trend for nanowire biosensors. However, please remind that our aim is here. How to recover these problems? Our solution is this one. So here is the sensing area. We have nanowires. This nanowire connected to the common source line via source gate, selector gate source. And the other side connected to a selector gate drain, and after that, eliminators. After sensing by the eliminators, we can count the address which nanowire sense the spikes. So by this way, we can introduce an independent sense factor. It is epsilon, M over capital N. By eliminator to work as a function to exclude the, leave the nanowires having signal from the BIOS spikes. Otherwise, nanowires, the other nanowires will be eliminated from the signals decoders. By this way, we have the chance to exclude the factor issues. So this is such kind of circuit is very analogous to semiconductor memory technologies. Sense amplifier, this one. Okay, this is similar to the sensing system of semiconductor memories. Okay, now next let's consider about the noise. We have to satisfy epsilon delta I must be larger than I noise. Noise comes from the non-specific signals. N, capital N can be determined by the silicon technologies. So M can be determined by interdisciplinary experiment, biochemistry, and silicon technologies. Okay, now here is one of nanowires. Okay, one of the receptor captures the spike. This is the first captures. Signal change a little bit. Time further has passed. Second one comes. Third one. However, if this signal change is so small, if it is sensitive or not, we are not sure. We still need to wait some time. Third one comes, fourth one comes, five one comes. Maybe someday we arrived at the real sensing. Time after time has passed. Good enough. What I mean, the number of captured spikes on the nanowire is sensitive to the sensing abilities, critical to the sensing abilities. Okay, if the sensitivity of the transistor is much better, in such a case, we can sense here. If the sensing ability of each transistor is not good, we have to wait until here. Therefore, sensitivity is also important of the nanowire. However, both LOD and detection times itself are different from the sensitivities. Sensitivity is also important. However, it is different from LOD and detection time. However, if the sensitivity is degraded, both LOD and detection time increases. Not a good scenario, this one. Okay, therefore, we needed to increase the sensitivity of the transistor itself. Okay, after resolving these problems, we can search each nanowires, signal of each nanowires, and we can get the stats of the signals. We may analyze these signals to determine whether or not the virus really exists. Now let's simulate these structures. These portions, we sandwich this portion sensing area by AC electrode. This is the AC electrode. Here is nanowires. Now we have about 400 nanowires in our simulations. This nanowires covered by the oxide, biocompatible oxide. On the surface of oxide, there are plenty of receptors. And dot depicts the floating biomolecules, that is spikes, target spikes. Okay, now this is a scheme of our simulation. We have used the Navier-Stokes equation without inertial forces. And also we combined this one with the Langevin equation with Monte Carlo. Monte Carlo used here. This is random force. Okay, you know, specimen electrolyte would be depleted like this from the surface. Now here is a depleted fluid, here is a fresh fluid. Inside the depleted fluid, there is a less concentration of target molecules, target biomolecules. This is not good. It is a disturbance to reduce the sensitivities, to degrade the sensitivities. We have to remove this one by using AC electroosmosis. But AC electroosmosis steers the depleted fluid, and like this. Now here is the surface of the sensing areas. So by this way, target biomolecule can arrive at the surface of the sensing regions. We hope to. Now this is the simulation result. Left-hand side without ACEO, right-hand side with ACEO. Please check these portions. We can successfully correct the target biomolecule spikes around on the surface of sensing areas like this. Okay, now this is the MC simulation result. Stats of the all of sensors, 400 sensors. G is conductance, delta G over G sensitivity in this case. Without ACEO, average white lines, 22%. With ACEO, average white line is 29%, more than 4 times larger, improved. Okay. However, we also still have the eliminator. Eliminator leaves most sensitive nanowires only. In this case, we can use these lines, not the averages. We can improve the LOD and sensitivity more than averages. If we eliminate the eliminator leaves only most sensitive nanowire, we may use these lines only or these portions. In this case, the sensitivity increased, raised up until 120%, and detection time further decreased, shortened by 50% from the average. Okay, now I have a discussion about the electronic virus sensor. It may take the role of IoT devices because we can get the sensing result, diagnostic result as a digital data. So by using digital processing, we can forward this data to the IoT network directly. After that, we may forward these data for AI and big data. Okay, by using AI with big data like this, we can expect that AI can optimize the medical resources distributions. This is my hope. Okay, now in summaries, now here is a worth. We may deploy such kind of biosensors, electronic biosensors. We can collect data all over the world about regarding the viruses, like COVID-19. And we can connect these data stacks of the diagnostic digital data directly to the internet. Via internet, AI collected such information, and AI can share such information with institutes of disease control such as CDC. And this AI can optimize the medical resource distributions. We can expect AI can optimize this one, medical resources distribution globally. And also we can expect AI can help to improve the sensing ability. This is the stats of analysis of the stats of diagnostic results, I think. Now here is the acknowledgement. Professor A. Kawaguchi from University of Tsukuba, Professor A. Teramoto, Tohoku University, Mr. T. Narita from Loras Corporation, Professor I. Kurachi from KEK, Japan. Thank you very much for your attention.
Thank you, Dr. Hiroshi, for your excellent presentation on the contribution of eradicating the virus from the usual, other than usual antigen antibody test. Here, the audience, are you having any questions from Dr. Hiroshi? Dr. Hiroshi, just I want to ask you one question. So in what way this electronic sensing for viral detection will be better than the normal antigen antibody detection method?
Charge. We want to detect the charge of the charge having charge carried by our spike.
Okay. No, what I'm asking, whether it will be a cost effective and then sensitivity. So in what way it is advantage?
Cost is not advantage, I think. However, these days, such kind of technology may be demanded than before, I think. Therefore, cost performance would not a big problem compared with before, I think. And advantage of this method is to control the LOD and the detection time by the design of circuit.
Okay, thank you, Hiroshi, for your explanation. I welcome others to ask some questions if they want any clarification.
Okay.
Audience, please come forward.
So just a minute.
Dr. Hiroshi, have you done any experimental work? So how do you make these silicon nanowires?
Pardon?
How do you make silicon nanowires?
Pardon, again, please.
How do you make silicon nanowires?
By using the process of NAND flash, similar to NAND flash.
Is it possible to isolate single nanowires for your electron?
So more practical version to be feasible with manufacturing should be not a nanowire. This is just like an active area used in the NAND flash, two-dimensional NAND flash. That is active areas. So how to say? So silicon surface is etched. Now here is some thin areas on the surface of silicon. Such area can work similar to the nanowire for this application. I think this may be more practical to the manufacturing because such a process already used in the manufacturing in the memory technologies.
Yeah. Thank you, Dr. Hiroshi. Rasul sir, I think we can get. Yeah. Yes, sir.
Thank you, Hiroshi, for your wonderful contribution for developing a technology to eradicate these viral infections. Soon, I hope your technology will be used across the globe. We wishes your research to come forward and then it will be utilized by our all the people. Okay, thank you, Dr. Hiroshi.
Thank you very much. Thank you very much.
Yes, thank you once again, Dr. Hiroshi, and thank you, Dr. Rasool, for honoring this session. Yeah, so we'll leave the session and join back at just a minute, 12:45, sharp 12:45.